So hello to everyone. My name is Milos Capin, and I've been working for about 7.5 years for HDL Design House in the field of analog design. And today I will show you some of the features and an overview of an analog design and porting in today's in modern circuits. So why are analog circuits important? They include things like PLLs, which are used to generate clocks. In modern systems, we have voltage regulators, which can create quiet internal supplies or can just lower the input voltage. We have I/O transceivers in all possible circuits like USBs, HDMIs, and so on. So the transceivers that drive the channel are analog. We have ADCs and DACs, which convert analog to digital and vice versa. We have a lot of voltage and current references. We have PRR circuits, for example, which detect the level of supply voltage and enable the system to enter the reset state when voltages are not okay. And these are only some of the examples. There are a lot of more circuits which are not mentioned here. So how do we design analog circuits? We usually work in Virtuoso schematic editor, and we use library components which are delivered by the foundry with spectrum models, layout views, and so on. From these schematics, we can generate symbols which can be instantiated in other schematics, creating a hierarchy. And for simulations, we create test benches which are very design specific. So this is the main difference between digital design and analog design. We don't have a uniform flow. We don't have specific test benches for every single circuit. We have very specific test benches for circuits, and the analog designer has to know the circuit, has to understand how it works, and he is the one who designs and verifies the circuit at the same time. So we don't have any kind of analog verification which can catch, apart from AMS modeling, of course, but those are that can only model some functional errors. We cannot catch any real errors in anything other than real spectral simulations. When we have finished creating our design, we can run corners, and we run front end of line process corners, which model the different threshold levels and different mobility of carriers in devices. So, for example, SS means slow NMOS, slow PMOS, which is the corner right here. And as you can see, the SS devices have the highest VT in both PMOS and NMOS, and those circuits are the slowest. So this corner would be the most critical one when it comes to high-speed circuits, for example. We have to run temperature corners. Usually this is set by the purpose of the chip or the actual design that we're working on. We have to change supply voltage. It's usually plus or minus 10% or plus minus 5%. But the corners apply the same process variance to all devices of the same type. And if you want to run mismatch simulations, so that is in those kind of simulations, we can see a mismatch between two devices. So when they do not have the same VT or any other parameter. And Monte Carlo simulations introduce random process variation and device mismatch. They can also be global or local. After that comes the layout, the physical layout. And all library components have their own layout view, which contains all front-end layers and M1. And we, layout engineer, actually creates a floor plan and routes nets which connect these devices. And we use DRC and LVS to check for consistency, to check for physical errors. And this is the same as with the back-end design. There is no real difference here in these checks, DRC and LVS. After that, there is a parasitic extraction. It has to be performed. It can usually be C only or RC only. And it extracts parasitic resistances and parasitic capacitances on the drawn lines. And here we also have some kind of corners those are called back-end of line corners. We usually don't run all of them in analog design. We usually choose the worst corner and run the design for that. We can use the extracted netlist in the existing test to verify the post-layout performance. So we run the same test, we just include the post-layout extracted netlist. And there are some other very specific simulations like the electromigration and IR drop analysis. It is a very important analysis in some cases, and it can tell us if some of the lines that we are drawn are too thin, if they can carry the current, or if the voltage drop is too high on them. So how do we design? How do we choose topologies, and how do we design circuits in analog electronics? Of course, the starting point is always circuit specification. This can be derived this can be received from a customer. This can be derived from some higher parameters, some system specs, or anything like that. Based on those specifications, we choose topology. And topology is usually chosen based on the experience or just scouring through scientific work or scientific papers or books, and I mean any possible source to derive a topology. And once the topology is chosen, we can start to play with the dimensions. And the main parameters in MOSFET transistors are channel width and channel length. And other separate parameters are DC currents. With DC currents, we can usually tweak the circuit to achieve, for example, a higher bandwidth, a higher gain, or anything like that. It's at the expense of power consumption, but it is a parameter that can be used to play with these outcomes. One of the biggest issues in modern analog electronics in SoC design is headroom in analog circuits. In analog circuits, headroom is set by supply voltage, thresholds, and operating regions of MOSFET. What is headroom? Headroom is the actual room for analog signal in which it can swing. So our analog signals cannot really swing from ground to supply voltage. So if, for example, if we have 2.5 volts of power supply, we cannot have analog signals. In some cases, yes, but usually we cannot have signals using the whole 2.5 volts. In this example, we have a differential pair, and this is one of the most basic building blocks in analog electronics. It's used all over the place in operational amplifiers, receivers, comparators, and so on. And it relies on balance between NMOS, in this case NMOS devices on the input, which are driven by a constant current source. Usually, these two voltages, V in 1 and the V in 2, are set at the same level, either by the feedback loop or in a case of some comparator. And in this case, the lower limitation for input voltages is the saturation margin of this current mirror, which is in this example 100 millivolts, and the VGS of this, actually of both of these NMOS devices, which are 400 millivolts. When added together, that's 500 millivolts, and our input signal cannot go lower than that. Now, if we don't take into account the limitations of the previous stage, which usually cannot go up to the VDD, it can go a bit lower, but let's say that it can go up to VDD. Our useful headroom in this case is 2 volts. And that's for 2.5 volts of high voltage supply. But if you go lower, if you, for example, move to another technology, which has the lower IO voltage, at 1.8 volts, the headroom is only 1.3 volts. And this is sometimes a very serious design challenge. In some cases, we can just port the circuit as it is. In some cases, we have to resort to using a new topology, which can handle this decreased headroom. In some cases, we have low VT devices, so devices with very low thresholds. In some cases, we don't have them. So sometimes you have to resort using PMOS and NMOS combination of input devices. And this is one of the biggest challenges. And for this reason, analog circuits can sometimes grow in size when moving to a new process node. So analog circuits don't really follow the Moore's law, and they don't shrink with technology same as digital circuits. This is one of the most famous examples, which is very often used in SoC designs. As I mentioned, phase-locked loop. It's often used to generate clocks, to distribute them to various blocks around the system. It can be used to multiply reference frequency, and the design of this circuit is a very specific problem. Design parameters are derived from a linear S-domain model, which can be implemented in MATLAB or any other programming language or software package that deals with PLL design. Usually, jitter is the limiting factor in design of PLLs. From jitter, we can derive phase noise plots, which we can then incorporate in our MATLAB model. And we use that to derive parameters like KVCO, ICP, which is charge pump current, filter transfer function, and so on. In modern communication standards, jitter spec is very strict, and this is usually the main design challenge when designing PLLs. In this case, so PLL takes the reference frequency and takes the divided frequency, which is divided from VCO output frequency. It compares these two frequencies, these two signals, and generates up or down signals, which are then converted to current and smoothed on low-pass filter to create VCO control voltage. This control voltage adjusts the VCO frequency so as to achieve the steady state in this system. And design of each one of these blocks is a completely separate task. VCO, it can be LC VCO using capacitors and inductors. It can be a ring VCO. And to simulate it, we use transient simulations. We use periodic steady state and P-noise, and so on. Divider can be a completely digital circuit. It can be designed as any other digital circuit. PFD is in its essence a digital circuit, but it's usually designed in an analog way because we have to fine-tune it to achieve these small peaks and to reduce dead zone and so on. Charge pump is again a completely analog circuit. We use again transient simulations to check its operation. We use noise simulations, and we usually don't simulate LPF. We just measure the transfer function using S parameters or something like that. And for final verification, we have to run transient simulations to see if the PLL operates at the desired frequency, if the log time is okay, and to verify the jitter. Here is an example of a completely different circuit. This is a bandgap voltage reference, which is universally used as a temperature-stable voltage reference. The design of this circuit is nothing alike the design of PLL. This circuit relies on a very interesting phenomenon found in bipolar devices and also in sub-threshold MOSFET devices. And that is the VEB voltage, which means difference between emitter and base voltage has a negative temperature coefficient, or CTET, complementary to ambient temperature. However, the difference in VEB voltages between two devices of different sizes has a positive temperature coefficient, or PTED, proportional to ambient temperature. And we can use this phenomenon to add these two voltages and to tweak them to achieve a very flat line, a very flat voltage across the temperature. This is not perfectly flat because we have second order and third order nonlinearities, but we can easily achieve a parabola with maybe 3 or 4 millivolts of difference between highest point and the lowest point. And as you can see in this equation, we have VEB2 and we have VT, which has a positive temperature coefficient, and we have some parameters which we can tweak to achieve this balance. Now, to simulate this circuit, we can use DC simulations to check the curvature of this plot, and transient simulation to check for startup. These circuits are very sensitive, and as you can see in this plot, this is a plot of the input voltages coming to this OpAmp. And they meet at 2 points. One point is here, and one point is at 0. 0 is unfortunately a stable state, and we have to push the operating conditions to basically lock the bandgap in this metastable point, which is a desired point. And to achieve that, we have to implement a startup circuit, and we have to simulate that circuit very carefully across corners and all possible conditions. Now, when it comes to layout, analog layout is a very precise work. Device matching is one of the main concerns. So, for example, if we have a differential pair, we want those two devices to be as similar as possible. However, we cannot guarantee that the manufacturing process is going to be perfect. We will have some non-uniformities, which can be in one axis, they can be in two axes, and so on. We have a lot of different things which we must care about. And sometimes we have to use dummies. Here on this lower picture, this is one of the examples of a good differential pair layout. This is a common centroid. This is not the only technique, but it's one of the better techniques. So if we had, let's say, M1 devices in the upper row and M2 devices in the lower row, any non-uniformity happening in the y-axis would affect those devices in different ways. So we use techniques like this to achieve that uniformity and to cancel out those effects. However, sometimes we have to use dummy devices. Those are the same devices as the active devices. They can have the same dimensions or maybe smaller dimensions, but we use them to surround our active circuits. And this is a big concern for area. Sometimes when moving from one technology node to another, we can basically move to a technology that requires a lot more dummies to function properly, and the area of analog circuits can increase for this reason. On these upper two pictures, we see a layout of bipolar devices in bandgap. So now the question was, how do we decide how many devices we want? What ratio between left and right bipolar transistors we want? Now, this is not something that's usually done using simulations. This is just done based on the layout experience. We want to have a common centroid layout, and we want to have that layout to be as symmetrical as possible. For that reason, we will use usually a ratio of 8 or ratio of 24, so we can have 3 by 3 or 5 by 5. Or for example, of course, we have a 16 4 by 4 ratio also in the game here. Now, when it comes to actual circuit design, how do we decide the dimensions of these devices. Of course, I haven't mentioned that, but we have capacitors, we have resistors apart from most devices, but we use them. They are the most difficult ones for design because they are active devices. When it comes to describing the ratio of current in VGS, there is a square law. We have a square law, but that square law is not applicable anymore in deep submicron nodes. In deep submicron nodes, we have to rely heavily on simulation. And in order to simulate, we can just run simulations in circuit. We can try to design circuit that way. However, there is a very useful methodology called the GM over ID. And what's very interesting is that transconductance efficiency is very similar across different technology nodes, which means GM over ID parameter. It doesn't change, it doesn't vary much across different process nodes. And we can use these plots, and we can plot on other small signal parameters like self-gain or transitional frequency or anything like that, and use these plots as a guideline to, let's say we want self-gain to be, let's say, 40 decibels, we want transition frequency to be 100 megahertz. We can use these plots to find which dimensions we need and what currents we need to have in order to drive transistor to achieve those parameters. And it's also very useful because it intuitively can show some effects which we know from formulas, but they are easier to understand when looking at plots. And this is a very useful tool also when porting from one technology to another. So we can use it to compare devices and to achieve the similar parameters. So that was all. Thank you very much for watching and listening. And if you have any questions, feel free to ask. I will be happy to answer them.